So in the last video, I didn't do much commentary. I figured that maybe I should practice a little more talking through these problems, drawing them out, and so on. So I guess these videos may have commentary for problems. They may not. But I'm just gonna do whatever I feel like. Given two roots. Well, this is a pretty common DFS problem, or commonly solved DFS. But basically, for each, we'll take P, Q. We have a stack. We'll push P and Q onto the stack. We'll pop P and Q. If they have the same values, we move on. But we append the left children, or the most left child of each tree, of the PQ pair that we're processing, and the right child. So those will just continue to be put on the stack, popped out the stack, and the same proceed through the entire tree. That sounds pretty cool. A tree is balanced if its subtrees differ in height by no more than 1. So this would be valid. And we can do DFS here, where essentially we need to get all subtrees. So we'll push a node and a visited flag onto the stack. This is we'll push these onto the stack, and if a node has not been visited, then what we will do is push its children onto the stack and then mark it as true. So the stack would eventually look like true. Node false. So if we have R as a root, A and B, then what we'll have is, you can consider this to be R. What we'll have is A, false, B, false. These are just tuples. And so when we pop, we'll be getting B and false first, and then it will continue to essentially get to the bottom. And then from there, once we get to the bottom, we're going to be working our way back up the tree. And each time we're moving back up the tree, you're computing the height. You compute the height of your local subtree to where when you're computing the height of this subtree, you already know the heights of your left and right subtrees. So then the height of this subtree is 1 plus the max of either your left subtree or your right subtree. From here, and yeah, I think that's about it. Make it through the entire tree, then we'll just return true. So if we get the visitor here, this is when we will be computing the lengths of well, we'll be computing the lengths. We compute the height of the current subtree by referring to the height of the children subtrees. But for now, let's just move on. And what we do is add the parent to the stack, mark it as visited, and then for the children, we'll add them to the stack without marking them as visited. If node is none, also skip that. So here, let height is equal to height.get. Here we do the comparison to check to see if, yeah, I kind of missed out in the drawing diagram, but basically when we're computing the left and right subtrees, we just compare if the difference, the absolute value of the difference of left and right. And if that's greater than 1, well, we break. So here, we'll have a left pointer and a right pointer. So what we're interested in is if prices at the index L is less than the price at index R, then we're going to be keeping track of a max somehow. Maybe we call this max P, as in max profit. And if the element at index L is less than the element at an index R, we compute the difference. So R minus L is equal to some number. In this case, well, for this specific case, well, let's just consider this first case. So since 7 is not less than 1, we're going to have another case, some sort of else, and basically L is equal to R. So, and then in our outer block, R will just increment by 1. So R R goes there. Well, technically L, let's move this. L goes here, R goes here. Now L is there, then we get to our outer block, right goes here. Now we're at the next iteration. Left is definitely less than R, so 5 minus 1 is equal to 4. Then our max P becomes the max of either 4 or current max P. So right now it was at 0, so this will be 4. Then we will increment. Do we increment R here? Actually, I think what happens is you just increment L. Yeah. So in this case, so now L is equal to 5, or L is equal to that index, and then R would move. Now we're at the next loop. L is not equal to 4, or L is not less than R, so then this will eventually move. 6 minus 3 is equal to 3, which is less than 4, no change there. 4 minus 3, no change there. I'm done. So that's basically it. What did I miss? Oh, I don't increment this. Clone a graph. We have a graph. Undirected. So, given an arbitrary node, can have a clones map, but Just DFS through this. Each time we encounter a node, we take its list of neighbors, ensure that they're inside of our map. Then we ensure that our clone of the parent has that neighbor clone added to its list of neighbors. What am I missing here? Don't seem to be missing anything. Maybe just this. Cool. That's about 30 minutes of practice. I'm a little tired today. I think I'll call it there. Gotta walk the dog. See you all next time.